Hello, friends, and welcome back to Technology Now, a weekly show from Hewlett Packard Enterprise where we take what's happening in the world and explore how it's changing the way organizations are using technology. I'm your host, Aubrey Lovell. And in this episode, we are looking at computers going fast, really fast. In fact, we're looking at a computer running at exascale speeds, a billion operations a second. We've actually covered exascale before in an episode of our sister podcast, Technology Untangled, which we've linked in the show notes. So why are we talking about it today? Well, the 63rd biannual list of the world's fastest supercomputers has just been released at the 2024 ISC High Performance Conference in Hamburg, Germany. And topping it are two exascale computers, both of which were built with HPE's expertise, and a whole lot of partnership and collaboration. In the number one slot, Oak Ridge National Laboratory's Frontier supercomputer clocked up 1.206 exaflops. In the number two spot, the Aurora supercomputer at Argonne National Laboratory officially broke the exascale barrier at 1.012 exaflops. So how do you build the next generation of supercomputer? Why? And what does it mean for the rest of us? Well, as you know, if you're the kind of person who needs to know why what's going on in the world matters to your organization, this podcast is for you. So, exascale computing has been a hard nut to crack. In the world of supercomputers, numbers matter. Megaflops, gigaflops, petaflops. We're on a seemingly endless push for more power and more capability. And it's not just for the sake of pushing the numbers of flops or floating point operations higher and higher. Demand is constantly growing in the fields of AI, material science, and physics for more accurate simulations, greater certainty and clarity, and of course, quicker results. The exa in exascale means 18 zeros. To put that in context, it can perform a quintillion operations in the time it takes to, say, one Mississippi. That is a lot. And so it's no surprise that breaking the barrier has taken years of work, a lot of resources, and a whole new way of looking at computers. Because of the staggering engineering challenges involved, there are very few publicly known exascale computers in the world. It's one of them, Aurora, we'll be talking about in this episode because we've been joined by Susan Coghlan, Project Director of the Aurora Exascale Computer at the Argonne National Laboratory in Lemont, Illinois, to find out more. Hi, Susan. So why did you build Aurora, and why is the exascale barrier an important one to break?
Well, the Aurora Exascale supercomputer, it was built at Argonne National Labs. It was part of the U.S. Department of Energy's Exascale Computing Project. And it was also our next big computer that we were bringing in. The project itself aimed at building and developing a new generation of supercomputers, and we needed it to perform at least an exaflop sustained, which is 1 billion calculations per second. It was designed to accelerate, of course, scientific discovery, innovations in various fields, including things like climate modeling and material science and biomedical research. So all of those kinds of things. So that's why we built the system. And if I talk a bit about why the exascale barrier was important to break, the US and also other countries around the world, of course, need the most powerful computing, in this case exascale, to maintain the scientific and the economic, and in particular national security competitiveness. So this is really all about competing within the world's markets and ensuring that we had the best technology for that. So exascale computing is really essential for the US to maintain its global leadership that we have in the science, the technology, and the innovation spaces. And having this kind of computing power at hand really drives that breakthrough that I talked about in many fields, the few that I mentioned, but it'll also accelerate scientific discovery by enabling scientists to simulate these complex phenomena that they couldn't do out in the real world. You can't really simulate a star going nova in the real world. So instead, you can do it though inside a computer. And being able to simulate those phenomena will lead you to breakthroughs in fields such as medicine and climate modeling and material sciences, batteries and designing batteries and things like that. And it does also drive innovation in fields people might not think of, such as in the finance and the healthcare and the manufacturing. And as I mentioned, it's important because it will improve national security. We can use exascale computing to enhance cybersecurity, optimize missile defenses, and simulate complex systems.
So who is going to benefit from Aurora's compute power?
So the hope is actually that the entire world benefits from Aurora's compute power. It starts with the science community, of course. They will tackle huge problems that haven't been possible on our previous supercomputers. Our early science teams that we always set up for our supercomputers before they're even built, we start working with them on their applications. And in our case, we've got some early science teams working on drug discovery, modeling the universe, and developing new materials for things like the batteries I mentioned and solar cells. To give you an idea of one of those scientific problems, we have researchers trying to understand the structure of the brain, which is a field I've always been very interested in. And they're doing it by mapping it, which hasn't really been done before. To do this, they need to map about 100 billion neurons. And those neurons themselves have quadrillion connections. So it's a lot, you can see. So right away, they are able to map a very tiny part of the brain. But with Aurora, they will be able to map much bigger areas. And having this ability to map, that's going to help them understand how their brains, our brains, work better and could even help us find new ways to treat brain disorders.
So let's break Aurora into its parts. What actually goes into creating an exascale machine?
Okay, so there's a lot. So creating and deploying an exascale computer is, as you can imagine, it's complicated and it's challenging. And preparing for a supercomputer such as Aurora has required years and years of planning and coordination between a lot of different communities and institutions. So between the computing facility, the Argonne Leadership Computing Facility, the vendors that are building and helping deploy the system, the science teams that I mentioned before, and also the ones that'll come once the system is in production, and then a lot of others. And if you look at just the system itself, talking about details, it has billions of components in it. If you start at the large, it has hundreds of racks, and each of those has many nodes inside of it. And then if you look at the nodes, they come in different types, some of which are very large, like the compute. We have almost 11,000 compute nodes, but it has thousands of other nodes just to make the compute nodes work. So you've got to have management nodes. You've got to have nodes where the users can log in and compile and run their codes. You need high performance storage to go with the high performance computing. And that's thousands of nodes in our system as well. And then, of course, all those nodes have to talk together. For that, you need networking switches and tons of cables. To give you an idea of scale there, Aurora actually has more than 300 miles of networking cables within the system itself. And then if you go down smaller, the nodes, the switches, they have components inside like processors and memory and networking cards and power distribution that you have to get all the power broken down to the level that's needed by each of those components. And then if you look inside some of those components, like the processor, those have billions of transistors within them. So at every level, we have many, many, many different things. And if you're going to run this very complicated supercomputer, it's going to need power and cooling to make it work. Aurora is our largest that we've fielded, and it's also our most powerful. And we ended up doing a lot of substantial facility upgrades to get ready for it. It takes up in space just the size of 2 professional basketball courts. It's thousands of square feet. And for that, we actually took the opportunity to expand the data center to accommodate it. And at the same time, we added mechanical and electrical spaces so that we could provide the power and cooling that was needed to support it. The new electrical room actually has 14 substations in it. So these are big monster power things, which I love, that kind of thing. And that provides 60 megawatts of capacity. Now, as part of standing up these state-of-art supercomputers, you have to consider a ton of different things. So this is not just within the architecture of the computer, which is complicated and you have to work with the vendors on, but this is about the infrastructure and things such as the weight of the racks, The weight of the racks for Aurora, our compute racks, are 8,900 pounds. They're on a raised floor. So you have to make sure the floor tiles can support that. You have to make sure the stringer system can support it as well. And in fact, you have to make sure the concrete core that's below that can support that kind of weight too. This is something that a lot of people don't think about when they're thinking about, okay, you're building a supercomputer, but you got to worry about the weight. And you also have to consider how you're going to get the power and cooling to those racks themselves, because it has to come into those racks. This is direct water cooling to Aurora compute racks. So that means it flows through the compute nodes and through cold plates right next to the components. So you have to think about how are you going to get the cooling to come in at the right flow, the right pressure, the right temperature. And then, of course, getting the water down to that level, you have to make sure you can move massive amounts of water. We have 44,000 gallons in our water loop. So it's a closed loop that runs just through Aurora. And that plumbing starts out in 30 inches and it goes to 4 inches where it comes into the racks. All of that's pretty complicated, and you got to manage that and make sure it's working properly. And you're designing and architecting that before you even have the system fully designed and delivered.
Wow. So this isn't just architecting a computer. You're almost designing a whole city with utilities, traffic, and buildings. How does it feel to actually look at that 40,000 gallon of water behemoth that is Aurora?
It's stunning, by the way, to look at. I don't know if you've seen pictures. It is a remarkable feat. Just walking through it is awe-inducing to me. It makes me feel proud that we've got it on the floor in spite of so many challenges, that it's up, it's running, we're getting great performance, and things are looking very good. Still got a ways to go, but it does leave me feeling really proud.
Did this require a new way of thinking about computers, or was it a normal supercomputer with a lot more parts?
In some ways, it is a traditional supercomputer, built with more, as you said. For example, our previous supercomputers, they all had nodes and networks and high-performance storage. They all needed pretty significant power, not at the levels of Aurora, but still a fair bit of power and cooling. But in other ways, Aurora does require new ways of thinking. For one, the accelerator, that's the graphic processing unit, GPUs, you might hear, is one of the most complex in the world. And the memory architecture is also pretty complex. It's multi-layered. It has on-die memory on the GPUs. It has on-die memory on the compute processing unit or the CPUs. And it has regular memory like you might see in your laptop or your desktop as well. So when the application teams need to lay out their data within the node, they have to take that into consideration, something that they haven't had to do in the past. And that adds to the stability challenges, it adds to the debugging challenges. And so you've got challenges at all levels. And then another place where we have something that's not the standard traditional supercomputer is in the storage space. Most supercomputers have a standard file system. But for Aurora, what we did for the high performance file system, well, storage system, I should say, is something called an object store. And it's a different paradigm in using it. So the users can use it like a file system. We've got tools and software that'll translate their regular commands over. But if they want to get the best performance out, and if you're using one of these supercomputers, your goal is to maximize performance. You need to use the paradigms that are involved and the tools that are involved in using it as an object store. And so, yes, it's a traditional supercomputer with more, but it's got some twists to it.
How does it feel spending the last few years leading a project that's never been done before and that's likely to change lives?
Aurora is something that's near and dear to my heart. I put many years into it, and I've been engaged from the beginning. I think it is our most exciting machine, and it's been by far the most challenging project of my career, truly. For one thing, delivering a computer at this scale in the midst of a pandemic. Aurora was built and deployed during that, was really challenging. I learned a lot about myself, and I learned a lot about how to adapt and deal with a lot of things were completely outside my control. So I learned a lot. The project has been fascinating. The machine is challenging. The science is going to be awesome. And I can't wait to see what happens with it. It's been very exciting.
Thanks, Susan. What an incredible story and an incredible achievement. And we'll be back with Susan in a moment, so don't go anywhere. All right, so it's time for Today I Learned, the part of the show where we take a look at something happening in the world we think you should know about. And today, we're talking about using the very small to navigate the very large. A test flight funded by the UK government has experimented with the use of quantum navigation as a backup and eventual replacement for GPS. GPS is an amazing technology, but it is very easy to jam because the signal emitted from its satellites is very weak. In recent months, several flights near Ukraine and Russia have had their navigation affected by what's believed to be electronic warfare countermeasure systems, though it's not known if the scrambling was deliberate or not. And it's not unknown for people to fit GPS jammers to vehicles fitted with trackers. The new system uses an incredibly accurate atomic clock and a bundle of atoms cooled to negative 273 degrees Celsius or negative 460 degrees Fahrenheit to precisely measure the movement and direction of the plane, tracking it from its original position. Because the whole system is embedded in the aircraft rather than relying on satellite data, incoming signals can't be jammed. The quantum system has its drawbacks, though. For a start, it's currently very large. There wouldn't be very much room left over for passengers on a flight, and the technology is still very much experimental. However, running the system in the relatively cramped, rattly, and unsteady confines of an aircraft in flight is a fantastic proof of concept, and it's hoped that the system can be miniaturized to around the size of a shoebox within a decade and eventually commercialized. Super interesting, right? Okay, now it's time to return to our guest, Susan Coghlan, to tell us more about the Aurora supercomputer. So, Susan, what happens next? Are there incremental improvements planned, or is it now just about opening up use cases and science?
Aurora's just getting going right now. First, we have to get the machine through acceptance. We have a suite of tests that are pretty challenging, and we use that to verify that the machine's doing what it needs to do, but also that it's stable enough that the users can get on and get their science done. And getting the machine ready for production is part of that. So right now, our work is getting the machine to that spot and then getting the users on and getting science on the system. And then hopefully getting it into production soon and opening up to the allocation programs, Insight and ALCC that we use to allocate time on our supercomputers.
So you're now the second fastest supercomputer in the world, officially. First of all, congratulations. You're going to be a top-ranked machine for some time to come. Was that a goal in itself or just a nice bonus?
Going to ask all these tough questions. To be honest, for me, and I think for the ALCF and Argonne, it's really just a nice bonus. Our mission is about the science, and that's what I always pull out when I'm talking to people. It's like, yes, all of that's true, but it's about the science. And the goal is making sure that we can do breakthrough science and engineering. And that's really what we want to focus on. Our goal is to provide those resources to the researchers so that they can accelerate their science campaigns. It's not to have the world's fastest supercomputer. And we know that there's not many institutions in the world that are going to be able to provide exascale resources due to all the things that I've talked about, the power, the cooling, etc. And it's important that DOE provide this for the nation and also for the world to help propel that science forward, because that is what we are about. It's the science.
And last question, why should our listeners be paying attention to Aurora and exascale computing more widely?
Well, I kind of touched on it, I think. But basically, Aurora is an immensely powerful scientific instrument. That's one way to think about it. And what's important to understand about it is this powerful tool. It's available for anybody to apply for access. You need to be able to utilize it, obviously, but it's available and open to the world. It's free from the constraints of the private industry, and Aurora is poised to really be a powerful tool for the scientists and the engineers who are working on improving our world. And I think that's That's what we want to see, and that's what our goal is.
Thanks so much, Susan. It's been great to talk, and you can find more on the topics discussed in today's episode in the show notes. Okay, we're getting towards the end of the show, which means it's time for This Week in History, a look at monumental events in the world of business and technology, which has changed our lives. Michael, I missed you on that section. The clue last week was it's 1906, come fly with me. A pretty straightforward one this time, I think. It was, of course, the patent for the Wright brothers flying machine issued this week 118 years ago. The formal name for the patent was New and Useful Improvements in Flying Machines, and that it certainly was. It was the outline for the first working powered aircraft. Their first powered flight had taken place in 1903 at Kitty Hawk, North Carolina, but despite being filed at the time, the patent wasn't granted until 1906. The patent not only cemented the invention of the airplane, it noted and formalized the perfection of many of the control surfaces and tools that we still use in aircraft today. There's been some argument over whether the Wright brothers really were the first to perform powered flight, but their patent was certainly the first to be formalized in the USA, and their legacy is still being felt to this day. And the clue for next week? We're going back to the 80s. It's 1987, and this picture got a lot of people animated. Ooh, I kind of think I know what that is, but I'm not sure. We'll have to find out next week. And that brings us to the end of Technology Now for this week. Thank you so much to our guest, Susan Coghlan, Project Director of the Aurora Exascale computer at the Argonne National Laboratory. And to you, our listeners, thank you all so much for joining us. Technology Now is hosted by myself, Aubrey Lovell. This episode was produced by Sam Data-Pollen with production support from Harry Morton, Zoe Anderson, Alicia Kempson, Allison Paisley, Alyssa Mitri, Camilla Patel, and Chloe Sewell. Our social editorial team is Rebecca Wissinger, Judy Ann Goldman, Katie Guarino, and our social media designers are Alejandra Garcia, Carlos Alberto Suarez, and Ambar Maldonado. Technology Now is a Lower Street production for Hewlett Packard Enterprise. And we'll see you next week. Cheers.